All right. So from tropical coral reefs to the cryosphere, we're going to continue this discussion about these climate elements. Sorry, can we get the slide up on the screen? I just need to click it. There we go. So the question I think we're asking throughout all of this work is, can we avoid surpassing these critical tipping points? We just heard from Andrea that we've already passed it for corals, which is, if you recall back to Julie's talk yesterday, that was so powerful that once you've lost something, you think about, could I have done a lot more to try to avoid that loss? And I just wonder if 20, 30 years ago, some of the things that were being talked about now for coral reefs were taboo, right? You got laughed out of the room from your PhD advisor to talk about them. We can't let that continue to happen with the rest of the things that we're going to talk about. So now we want to transition into the cryosphere. And I showed this graphic earlier, which are these tipping points in the global system that pose big risk to the stability of the climate. A number of them are in the polar regions, and I didn't include land ice, but I think it might be on here, or glaciers in the Himalayas, which Leslie's going to talk a little bit about. But the point is that a lot of these critical tipping points are polar, and that's because the poles are warming faster than the rest of the planet. In the case of the Arctic, there are even more risks just because of this whole issue of positive feedback. So we know that Arctic sea ice is moving along a trajectory of change faster than almost any other part of the system, maybe other than coral reefs. But that has this knock-on effect of accelerating other changes. So as you lose the loss of summer sea ice, you are losing that albedo effect. The open ocean is absorbing more water. That's leading to this Arctic amplification of really rapidly rising temperatures in the Arctic. That is leading to a whole bunch of things, sort of unintended consequences. Fires in the tundra, right, that are a positive feedback loop. Methane seeps, which are increasing all across the Arctic. So, and a variety of others. So there's really ample reason to think about and ask the question, can this be slowed down? Because if we get to the point where we're having conferences and we say, well, that all tipped, we might not even be thinking about our world in the same way. And the heat that we're trapping is increasing. I just want to highlight that. It's not stable. It's not just a steady number. It keeps going up, right? So this amplification and this heat is only going to continue. And so, there's no way out of here, right? This is the planet we have, and we're either going to have to save it or sink with it. So we have a number of talks here that I think are going to be super interesting. We're going to start with Leslie Field, who has been working on this issue of ice for quite some time. She founded the Arctic Ice Project. It was called, Ice 911, I think, when it was started. She's now pivoted to some other ice explorations, and she is going to talk to us about that. So Leslie.
Thank you so much, Brad. Yeah, thank you so much. It's a privilege to be here. To advance, what am I?
That green clicker on the.
Aha. All right. Can we survive without the cryosphere? Probably not well. Does this one?
The green one.
Middle, up here. So it's an emergency, and you've been hearing a lot about this, so I think you've probably got the message here. Failure to act has already embedded us with a lot of grim realities that we're facing right now. This is from NOAA, and if you look at how much it's been accelerating, this is taking from the same data from this NOAA study. Basically, everything's accelerating. What we had as an average from 1980 to 2021 is dire, $2.155 trillion of damages in the US alone and over those decades. But then when you look at 2021 alone, much higher rates of deaths and damage than in each of the previous periods, average or years. So it's bad. And we know a lot of what happened. In fact, Exxon, or Humble Oil, which was the predecessor to that, used to advertise that they were making enough energy, they were dealing with enough energy to melt, 7 million tons of glacier. Wow. What I wanted to show you is this relentless decline of what's had me starting Ice 911 that then became Arctic Ice Project, this relentless decline of ice in the Arctic over time. And you're looking at is this a pointer then? Aha. You're looking at how much sea ice over 4 years old is here, what the month and year is, what the sea ice age is. This has been recolored from satellite observations by NASA. Best video of this I've seen. You'll notice a few things. We used to have a nice high inventory of a bright reflective ice shield up in Beaufort Gyre, up in the Arctic Ocean. And we had an ice export going along through the Fram Strait near Greenland. I'm going to let this click on for a bit because there are several interesting things. The more you melt multi-year ice, the more you're rebuilding ice on young thin ice, or heavens, open ocean. We're still lucky enough that we're reforming ice every winter, yay, in a lot of spots, but it doesn't come out as bright because it takes years to build up that multi-year ice to that higher brilliance, basically. Also, as things get less, we get much more ice export over time, and it just gets worse and worse and worse. I think in the interest of time, because I understand we're behind and I have a lot to say, well, the next few years are pretty critical, where you start to see that because these are positive feedback loops and the more it happens, the faster it happens, the less multi-year ice you have, till you've got almost nothing left. I guess we're going all the way through the whole 2-minute video here, till there's almost nothing left. That's a bad spot to be. And if you're like me, an engineer and an inventor, and you want to do something so that your children might have a prayer of a habitable world, you start thinking, wow, that's a tipping point. That's a leverage area. Maybe I could do something about that. It doesn't look like under current conditions there's a natural way back. I wish there were. So you get as close to nature as you can, and then you start thinking, okay, here's the before and after. You're getting to see it again. There was a lot, there isn't much. This is a terrible tipping point. As Brad mentioned, one of the big risks here as we melt things is we get to release more methane. That's not good either, because over the short term, and many scientists now think we've got maybe 3 to 10 years to make the difference we need if we're going to make any significant difference at all. That methane is, many numbers depending how many years you're counting, but maybe 80 times more devastating, more heat-provoking than CO2 over the short term. So this is a big deal, and one that I don't think we've heard a lot about in this meeting so far, but CO2 and methane, both terribly important. And therefore, if this is such a dire thing and a positive feedback loop and a potential tipping point, it also becomes a crucial potential lever to do something about it. So that's the motivation of what I do. You need a lot of framework considerations. I'm going to race through some of this because people have talked about this a lot here, and I so appreciate this. You need to really figure out, who are you solving for? Who are you solving with? Who needs to be engaged? With whom can we collaborate? And I'm here because I really want to seek further collaborations and further knowledge. There's a lot to it. It isn't just the engineering. Why focus on albedo? Historically, that cryosphere reflected a lot of incoming solar radiation for free. We didn't do anything to deserve it, but it's been a wonderful bonus to us, and now that we're losing it, we're accelerating things by maybe as much as 1.5 times faster global temperature rise than we would have had from the CO2 effects alone. Big deal. Advantages of localized interventions. I've always wanted to do something localized on the surface so that if you can see that there's some sort of negative impact, you can deal with it right away rather than something a little more global and diffuse. Seems faster to do it. And I've been an engineer long enough to know there's always an unintended consequence. It's just, what is it? So plan for it. Figure out what you would be able to do. This is what we've been doing for years now. On a pond in Minnesota, a homeowner who is a brilliant scientist and his friend who's another brilliant scientist have been doing rigorous work here on trying to preserve ice in his pond. So here's what the ice looks like untreated. Here's one that was about to be treated, and here's a treated area. Small stuff, about 100 feet across. But it has shown that it works. And Immediately, ice, just bare ice, looks like this. As soon as we put on our material, it looks a lot brighter. Here's snow. You can't do better than snow, or almost can't do better than snow. So that's nice. It's immediate. You could do this on thin Arctic sea ice if you got permissions. We have never gotten permissions to work on sea ice, but we can model sea ice, and we've been working with expert collaborators who show that if we treated part of the, I meant the other way. If we treated part of the Beaufortshire, we could preserve it longer. If treated, if we treated part of the Fram Strait, we could preserve it longer. And so those are very interesting things to know. And you get to, through climate modeling, see, are you going to have some unintended consequence somewhere? If I had more snow and ice here, would I have a drought here? Somebody besides the people coming up with a solution need to make those decisions of what's smart. Here we were working on a pond with full permissions and transparency up in Utqiagvik, Barrow, Alaska, with some of the folks who live there and some of our own crew, setting up instrumentation to be able to measure things. Here's what we've done on the pond. It's, we do very detailed work, trying to measure everything, coming up with a thermodynamic model. And we have shown that we don't stop ice melt entirely, by no means, but we decrease the melt rate, and that's a big deal. And this is drone footage of this pond that's been segmented in that same property, half treated, half not, so test and control, so that we can tell what we're doing. So here's the answer to what can you do about it. You can think about things that are testable in a way that can't harm anything and see whether you've got a solution that works. I've been an engineer long enough too to know that in theory, there's no difference between theory and practice, but in practice there always is. So it's essential to be able to test and refine and figure out what you're doing. Recently we were asked, last year we were asked, could we use this on glacial ice? We're invited to India to work on actually 2 sites now potentially to see if we can help with glaciers. The solution that we had for a flat pond is not the same solution that we will need for this. So we've been working very hard, again in Minnesota, was just there a week or so ago, checking the site, looking at other materials we could be trying that are equally safe. But these are a big deal. When the Himalayan melt, we're risking the water supply of 1.6 billion people, and it's actually the food supply, those 10 rivers that are having their flows compromised, is really representing the food security for a third of the world. Some of these have been very surprising facts to me. Pakistan has been a third underwater, a third of it underwater with huge floods. Again, these are all tying together. The reflectivity from the Himalayas matters to the planet just as the reflectivity from Arctic ice. And so we're planning collaborative testing. If you want to know what we need funding, we need permissions always. And we've been working on the permissions well. It looks like we're well on the way to getting that in India because they've asked us, so that helps a lot. They're melting at an alarming rate. There's a lot of satellite data that shows that's true. I know there's some counter information that said, but no, they're actually melting up there. And Greenland is losing lots of ice. Now, one of the problems with Greenland, as I'm sure you know, is when you've got land-based ice melting and it flows into the ocean either as big chunks of glacier or as meltwater, you're raising sea level. So you're also then putting at hazard all those coastal communities in the world, and there are many. And many of them, cannot afford to be building seawalls and such. So it's a large problem. Had we time, and I think we do not, there's a beautiful video that you would love to watch. Look it up on YouTube, Chasing Ice, with the largest single calving event put together by James Bailog, who founded this Chasing Ice. Lovely, it'll make you cry, we cannot watch this. It takes many voices and many hands to make the change we need. This is from what I tell my students at Stanford. It's not just the engineering. We need everything else that you've been talking about here. And let's please help each other. Let's please collaborate. Thanks very much. I'm pretty sure that was last slide. Yep, thank you.
Thank you very much for that. So now we're going to bring Kelly back to talk about a question that I asked her during the session, which is, can we do something at a regional scale? And she's going to talk about reflecting sunlight to preserve the Arctic.
Thank you very much. So I am back. For those of you who are in the plenary, you got a little bit of taste of the sort of form of intervention that I'm going to talk about. If we're looking at polar ice and the cryosphere more broadly, we have a really significant scale problem. Obviously, it's a big target that we're aimed at to change the sort of warming conditions which are outpacing the rest of the planet because of the way that heat circulates in the system. And so when we think about, the kinds of interventions that might help preserve or even recover, say, Arctic ice, then we have an issue of scale, and we also have an issue of a highly interconnected system. One of the reasons we want to preserve and restore the ice is because those interconnections create benefits for the rest of the system. Similarly, the warming that's happening in the rest of the system is highly influential on what happens at the poles. And so, as I mentioned in the plenary, one of the most, promising candidates for removing heat from the system at the kinds of scales implied is the reflection of sunlight, as Leslie mentioned. And the reflection of sunlight from clouds and particles in the atmosphere gives you a big magnifying effect and scale opportunity that's hard to replicate any other way. And so, these techniques for solar radiation modification at the cloud layer, low cloud layer, or in the stratosphere are potentially significant when it comes to looking at polar intervention because of the scale, because of the speed, and because maybe there is a way to target them more closely to look at the poles. Let me see. There we go. I mentioned before in the plenary, why scientists think that these things might be likely to be helpful. As when very large volcanoes go off, like Pinatubo erupted, there was a recovery of Arctic ice that was measured. And this is from the dispersal of particles in the stratosphere. This was a global effect that had a particular useful effect at the poles. And so at the global scale level, when you cool the planet, you get this effect on the poles. One of the questions that's come up recently and quite prominently is, could you do something more locally, particularly in the low cloud layer, to produce a more localized cooling effect that helps preserve or recover Arctic ice? And again, this is based on the idea of dispersing sea salt mist into low clouds over the ocean to make them slightly brighter. And at a global scale, this involves targeting banks of clouds, at least in the original concept, marine stratocumulus clouds, where they occur in a targeted way. So you get these spots of warming that then push out enough heat energy to create a global cooling effect. And so recently, quite prominently, scientists have proposed that maybe you could brighten clouds over the Arctic, in the Arctic region specifically, to produce this kind of effect in a way that's really helpful. And so, they've started to do some math around brightening clouds locally to see what that might look like. As that's happening, and I'm going to talk about, we've got some gaps in what we know and the capabilities we have to actually do that problem. And so Jim Haywood is a senior climate scientist at the UK Met Office who works on building the climate models that can do these problems in atmosphere models. And right now, our scientific ability to do these problems is weak. And so it's very hard to answer the question of whether you could brighten clouds over the Arctic and produce the kind of effect you want in a way that's useful. And one of the reasons that scientists are concerned about, jumping the gun on that idea is that these teleconnections in the way that circulation in the atmosphere and climate system works. And in particular, a really big feature of the system is that warming travels from the equatorial regions to the poles. And so the warming in the system moves to the poles. Even if you cool the poles, you'll have the warming moving in. And so local type effects of cooling or local type effects of sunlight at the poles are not the biggest warming source. And so local type effects to reflect sunlight are not necessarily going to overcome where the warming is coming from. And so quickly covering, just a few studies that, again, I'll emphasize that research is very nascent and the tools that we have to do the problem are not strong enough. But in the nascent research and early idealized studies of reflecting sunlight from the stratosphere at a global scale, consistently showed an improvement of Arctic ice relative to different warming scenarios, especially the warmest business as usual scenario for climate change. A more recent study that started to target the polar regions by injecting into the stratosphere in a way where there was a more localized concentration of particles at the poles. That showed that some localized possibilities are there, even in the stratosphere, but the effects are global. They're certainly not contained. And that's a bug and a feature of that. So, in general, if you're making a scaled enough effect to help the Arctic and polar regions, you are generating a global effect. And so the question is, what's the optimum way to do that? This is a very early study of marine cloud brightening. Again, marine cloud brightening implemented in a way that was designed to generate a global effect by brightening in different spots of marine stratocumulus, not in the polar regions, but produced a recovery of polar ice. Again, very early, very nascent. More recently, and again, in the past few years, there have been, more sophisticated simulations that are starting to emerge. And more recently, there are studies of marine cloud brightening from the UK Met Office Hadley Centre. But in general, what they're finding is that for both the low cloud brightening and the stratospheric effect, that the impact on sea ice, the big determinant is global mean temperature, not the local effect. So, where does that leave us? It leaves us, as Brad pointed out in the plenary, and if I could get my path going, it leaves us with a lot of questions and really a need to rapidly build and evolve our capabilities to do the problem. Because where we are today is we have some strong indications that for both in terms of scale and in terms of benefits in polar ice, in addition to various other climate impacts, that these techniques are really promising candidates. At the same time, we have deep weaknesses in our ability to do the problem. And they're in two broad categories. One is actually our ability to simulate the phenomenon happening in the polar regions well enough, particularly around some of the escalating feedbacks. And we have real weaknesses in our observations under ice at the surface in the low atmosphere in the polar regions, where improving that would really help our ability to do this problem, particularly in an environment of rapid change and unprecedented change. So we need more observations, and with those observations, improvements to the models of the targeted regions that we're looking at in the poles. And then we need the ability to actually better simulate these interventions and how they move through the climate system as a whole, which involves both, directed study of these climate interventions, as well as improvements to our ability to project and model climate. So that's a pretty big, ambitious thing to say. If I really wanted to answer the question of could I do, a scaled perturbation of the atmosphere to help preserve the poles, and this is potentially one of the best candidates for doing that, then what kinds of investments and activities do I need to undertake to do that problem? And we would say, we need to work on those things aggressively. So I'll summarize by saying that local intervention is not required to cool the poles and may actually face challenges in overcoming the circulatory effects that happen and warm the poles. And that the current state of the art is that simulations are pretty simplified. We have really a lot of work to do if we want to answer these questions better. And that means we can't rule out certain localized things either because of the state of our uncertainty. But this is where we are. Thanks very much.
Great. So for our final speaker of this session, I'm really delighted. Well, let me just preface this. I said in the beginning, I've asked this question a lot. Can we do anything about this? And so Ocean Visions is really interested in trying to answer that question. And there are potential interventions that range from very, very small to very, very big. Kelly and Kelly's been talking about things that are very big. Leslie, sort of intermediate, big and intermediate. There are things that might be smaller as well. And a good exploration would really would look at everything, much like we've done in the roadmaps that we created for CDR technologies. We now would like to do something similar around these different tipping elements. And I'm really delighted that we have hired, our most recent hire at Ocean Visions is Dr. Carrie Nichols, who came to us from academia, another journey story of academia to working directly on risk and solutions. So we're really excited to have her with us. She's only been on board a couple months, and she's going to talk a little bit about the work that she's going to lead.
Thanks, Brad. Great. I'm excited to be here today to introduce the newest work that Ocean Visions is engaging in on marine ecosystem repair and regeneration. So this falls under our 4 Rs, our programmatic initiatives of Ocean Visions of reduce, remove, repair, and reach. And I'll note here that repair and regeneration are working titles, although I've heard some recovery words being thrown around, and I think that might also be a nice R. So you've heard today about disruptions facing the ocean climate system and the fact that ecosystem transitions are likely to happen even if we cease emissions of fossil fuels today, as well as dramatically increase the pace of carbon removal. So unfortunately, as you've heard, we're sort of at this point where we really need to ask ourselves what the possible options are to prevent climate disasters. So, we really need to take a deep dive into this question, which is what are all possible interventions that could forestall devastating changes to critical marine ecosystems? So, oopsies. Getting a little ahead of myself here. So at Ocean Visions, we're beginning this new area of inquiry and assessment, first with Arctic sea ice because of the rate at which it is being lost, as well as its importance to the stability of global climate. And we're going to approach this by asking what are, all of the possible interventions that could forestall these devastating changes for that particular ecosystem, to identify the possible contributions of these different interventions or tools, assess their impacts and risks. And this work will be done under the guidance of an advisory board that will include diverse and backgrounds and perspectives from the Arctic region. So what we'll be doing is identifying all of the potential tools and interventions from globally implemented to regionally focused, as Brad mentioned. And we're going to assess and characterize their stage of technological development, the state of the science, including, have there been modeling studies done, have there been field or lab experiments, and what those results show. And also identifying, what are the possible contributions that these different technologies or tools could impact in terms of both their scope, so where and under what conditions, as well as their scale. So what magnitude of contribution might we see? We'll be identifying impacts to ecosystems as well as communities, as well as risks, such as potentially the ability for an intervention to be terminated. And I'm also really interested in thinking about the potential interactions between interventions were they to be deployed simultaneously. Through this, we will identify knowledge gaps and research priorities that can, further our understanding of these tools and technologies, as well as governance considerations. So a goal is to determine what further research, testing, and development would be needed to determine the potential efficacy of these different tools and interventions. And as I mentioned, this work will be guided by an advisory board, which will be inclusive of a broad range of expertise and perspectives, including scientific experts, Indigenous people, and community members, and also making sure that we're being inclusive of the voices of younger generations. Now, I want to make it clear that Ocean Visions is not advocating for deployment of climate interventions. Rather, we believe it is prudent to do a full exploration of all of the potential options to avoid climate disasters. So in this case, that means exploring the full range of these interventions that could potentially prevent the loss of Arctic sea ice, so that decision makers and community members will know if there may be, or at least have some approximation of if there might be reasonable things that could be done if needed to avoid these dangerous feedback loops that will have global impacts. The Ocean Visions Arctic Sea Ice Preservation Roadmap will sit on a digital platform similar to that of Ocean Vision's carbon dioxide removal roadmaps that we've been talking about the whole time here at this conference. And so having this digital format allows us to continuously update these roadmaps as science and the governance develop. And in that way, it really focuses energy and attention on the research and development needs as our understanding progresses. I'm in the very early stages of this week. As Brad mentioned, I started about 6 weeks ago. But at this point, I've mapped out a subset of the technologies, and I've also been having interviews with thought leaders and experts. Now, I want to take a moment to really acknowledge the moment that we're in, because it's very challenging. And almost nobody that I have talked to so far in this work has really wanted to deploy any of these interventions. But everyone agrees that we really need to explore these potential options and begin to have a conversation about them. And I want to stress that it is absolutely critical that that conversation is inclusive. If you or your organization are interested in this work, or if you have suggestions for other people to include, then please let me know. And thank you so much.
Okay, we have a break coming up, but I do want to give the opportunity for people from the audience who haven't had any chance yet this morning to ask any questions or make any comments. It doesn't have to be a question. If anybody wants to ask a question or make a comment, please do. There's a couple of mics here, and feel free to come forward and do that. And if there's any online also. Oh, okay, please.
Diane Thompson, University of Arizona. I'm curious about, I'm really excited about these potential interventions in the Arctic, but I'm curious about the stratospheric ones and the potential for them to exacerbate the temperature gradient in the poles, and thus the sort of trend we've been seeing towards more positive both southern and northern annular modes, and the potential for that to have downstream impacts on water resource availability in parts of Europe and South America and others that are impacted by those trends. So I know that's a very specific question, but we have really good modeling and paleo evidence that would suggest that that is a potential problem. And so is there a sort of observations of that might be helpful in that space? Thank you.
It should work. Yeah.
So it's a great question because looking at these global interventions, hydrology is probably one of the biggest target impacts for exploration. And because the modeling capability to look at the questions has been really nascent, some of the earliest data sets associated with simulations, they go from turning on and off the sun to models that model the stratosphere, but without the chemistry. And so, so it's evolving very quickly, and that it appears from the way it's evolving that where you do it, how you do it, and what you do it with actually matters a lot. And so there are possibilities that you can minimize some of these effects, and that some of these effects relative to warming still put most of the planet in a favorable place, including even with some of the changes in hydrology. But what I would say, I'll kind of refer back to the metaphor of medicine, is that this isn't something you would do if you were on a stable trajectory. It's something you look at relative to the trajectory for warming only. And in that context, then figuring out what is the optimum trajectory for this type of perturbation, what is the best you can do, and how does that compare? And that's really what I'll say to you is like the questions that you're asking, I would say like we're just not in a good enough position to look at them well enough.
Great. Next question, please.
Hi, Marissa Hughes, Johns Hopkins Applied Physics Laboratory. I really appreciate the research roadmaps that you're putting together and looking forward to diving deeper on those. And I'm wondering where artificial intelligence methods might start to fit into some of those research roadmaps, especially like there are a lot of emerging capabilities in accelerating models, targeting observations or interventions, and really characterizing the high dimensional dynamics of these coupled models and spaces.
Carrie, you want to take a crack
We've
at
done
it?
some work on that actually, or some of the research that we funded have. And so I'll speak to especially the atmosphere climate interface questions. There are two really interesting places right now, I think, for AI/ML. One is in looking at observational data, especially on clouds, which are really hard, the cloud atmosphere problem. And so there are some really recent studies out of Oxford looking at cloud aerosol effects with AI/ML. The other place that's really amazing is looking at big Earth system model data sets and just letting the AI/ML look for things that humans wouldn't see. And what do you detect and what relationships are there? So those are a couple of starting points that are really exciting.
Thank you.
So I would just add to, in terms of the research roadmaps, one of the methodologies is to mix up a lot of disciplines in the assessment of the technologies. And we've been having a discussion about how do we get AI experts to come into our space and hear our problems and challenges and then talk to us about how they might help synthetic biology, robotics, et cetera, because it's going to take a lot of different disciplines that in order to come up with things that are going to have a chance of being effective. So we're very much interested in that kind of mashup of disciplines. And some of that's happening here. Thank you. I recognize you.
Good morning. First, just a quick question. I think the AI could also be very useful as a way to query roadmaps and all the documents that are being put together. I think that it's a nice application. But my question was really for Leslie. I know you've been working a lot on this sea ice restoration and many years now, and I'm wondering if you could share what have been the challenges to just see this become a reality, and whether you really think there's a prospect for this to happen in the future.
All right, good question, right? And I guess we'll make sure you can actually hear me. So the biggest challenge for Arctic sea ice, or one of them, has been that we've never gotten permission to work on sea ice. And so for somebody who believes you actually have to test what you're doing to figure out whether it works, that's a problem. We've gotten to work in seawater in a standalone pool up in Utqiagvik with the folks up there helping to make that work. That was actually during the pandemic, but we could not get permission to be in the ocean. We've spoken to the IMO years ago, at a scientific meeting they were having in Chile. They appreciated our presentation a lot, but they warned us, international treaties, it's going to take that. It was post the Marine Dumping Act, right, that came into place some time ago. And so that's a problem. So we've done everything we can on a pond, right? We know what we can do. It's a natural type thing of keep ice where ice should be is really, where historically is really the aim of doing this in sea ice. But when we got invited a year or so ago to consider glaciers, it's like, heavens, yes. That's a really interesting thing to do. We're having to pivot our solution to use, but it's also, we've done a lot of proof points along the way on the sea ice of, well, albedo modification at the surface really looks like it'll work. There's been climate modeling in specific regions. There's been larger scale climate modeling. There's been all our testing on pond ice and a little bit of testing on actual seawater, turning into ice, isolated. So we know that we've got a workable solution, but I don't know when we'll be able to deploy that on sea ice. But I think the Himalayas or Greenland are good routes to demonstrate, let's pick up if there's any unintended consequence that we need to know about before we get out in our oceans with this. It's a beautiful place to do that. Everything we've seen says things are safe. We've had experts looking at it. We'll have more. I'd love more experts looking at that. We've pivoted our materials a little bit for Himalayas, but again, the concept's going to be the same, and we'll keep on working with the material that we think is probably the most promising for sea ice. So yeah, it's been stalled out in a way, but I'm excited to move ahead. And it looks like we can move ahead potentially this year. So thank you.
All right. We are at a moment for a break. I know everybody's been sitting here for a while, so let's get some coffee and tea. We have one last segment of this track, which is really interesting. It's all about the ethics of this work. And we'd love you to come back in a few minutes. I think we have about 10 to 15 minutes for a break, and then please come back and we'll hear from a group of folks about the complex ethics. Thank you all.